Well, fill in the food.
Well, the holidays are coming up, so. Let's see. Lights.
Oh, that
There
is
we
a
go.
light.
Okay. So we're going to start today. Like I said, this is going to be a 2-week chapter. We're going to spend the majority of this week on substitution, and then we'll spend a majority of next week on elimination. Some of the things that we've done, people had some questions about solvents. Why this solvent? Why not that solvent? Some people probably noted that certain reactions used bromines and iodines and others used fluorines. And we're going to get into why we see those specific trends. So the first reaction we're going to look at is going to be the Sn2 Style reaction. And what this stands for is Substitution Nucleophilic. And the 2 is what gets people quite a bit of the time. What this means is that this is bimolecular, meaning, and we'll get into what that means mechanistically. What it doesn't mean is that it's 2 steps. So this is one of the things people get confused all the time. This happens to be single step for determining the rate of reaction. So people see the 2, and you get that classic multiple choice question and say, hey, Sn2 reaction, what's false about this? Somebody will wrongly think that this is because there's a 2, that it's a 2-step path to the limiting step. This happens to be single step. What it is bimolecular. And so what that means is, let's take a look at the kinetics for a second here. So if you have some generalizable methyl bromide plus hydroxide, this is going to react to form methanol. And bromide. If we were going to describe this particular mechanism, we would be able to say that the rate of the reaction is proportional to the concentration of the alkyl halide, in this case the methyl bromide, and it would also be proportional to the nucleophile, in this case, or hydroxide. So both the amount of the initial alkyl halide and the amount of the nucleophile matter in terms of determining rate. So if we want to actually figure out a rate expression for this, we can substitute K, our rate constant, which gives us our degree of proportionality. And this would be our rate expression. So both of these concentrations affect the rate of reaction. You can drive the rate of reaction by increasing this, or both. If you double this concentration, it doubles your rate. If you double this concentration, it doubles your rate. If you double both, it quadruples your rate. So that's what the bimolecular means. It has to do with the fact that you have 2 different species that impact the rate of reaction. When we look at the Sn1 reaction, it's going to be unimolecular, meaning only the concentration of a single component of the reaction will affect the rate. So let's see here. Quick refresher on K. If you have a large K what does that mean? If you have a small k, what does that mean in terms of rate constants?
Large k means the rate proceed in the forward direction, small k means it proceeds in the reverse direction.
And if you have like a, let's say,
Are you talking about energy? Are you talking about the energy transition or which?
that also gives you some insight into the magnitude of the energetic barrier to the transition state. Exactly.
Is it
So it's both.
is it the ratio of like reactants?
Right. So for
Products or reactants?
I need to.
Like this, like
So for any general reaction, the equilibrium constant in this particular case, and this is just an equilibrium expression of K, would be your concentrations of C adjusted for C, D adjusted for D, A to A, B to B. So that would be your equilibrium expression. This is your reaction rate, your reaction constant. So this is saying it's going to progress at what degree is it going to progress towards products or reactants, but mostly this is just your degree of proportionality. So if you have a large K, the rate of reaction will increase more quickly as you have more substrates. If you have a small K, the rate of reaction will be less affected by the concentration of your substrates. And that's driven by the magnitudes of the energetic barrier that you have to overcome. So if you have gives you a little insight into what kind of energetic barrier you have. If you have a large energetic barrier, you're going to have a smaller K. If you have a lower energetic barrier, you're going to have a larger K. So let's just jump in and start talking about the mechanism for the Sn2 reaction, and then we're going to talk about what that means in terms of predicting outcomes for the reaction. The book goes into, and most books do this, they talk about evidence for Sn2, and they give you several paragraphs about evidence. And that's an interesting way to do it, because you get to have these little aha moments, like it corroborates the evidence, historical evidence. But I prefer to just lay out the mechanism, and then we can talk about why it agrees with evidence. We don't have to reverse engineer it that way. Okay, so for that exact reaction, we've got our hydroxide, we've got our methyl bromide, and what's going to happen is this is going to be our nucleophile. It's going to attack the methyl. This is going to push this bromine off. Give us our methanol and our bromide. I really, really suggest, having read some people's mechanisms, people did some very creative mechanistic work to try to justify motion of electrons, which there was a lot of improvisation. Keep the mechanisms. Try to practice the mechanisms so they look like the mechanisms in the book. That's probably the best advice, because there's a rationale to it. So try to get the mechanisms to proceed with the same logic in terms of the arrow pushing. Some people started combining multiple things where instead of breaking the mechanism out into steps, they would do an arrow, then they do another arrow, then there'd be another arrow, then there'd be another arrow, and then there'd be a product. And that's not a really good descriptive mechanism. You want to have a mechanism that makes sense in terms of discrete steps. And this happens to be a fairly simple mechanism. So what this requires specifically is backside attack. So this nucleophile has to approach this particular electrophile with a very specific orientation. And what that looks like, let's see here. This nucleophile has to approach directly behind, linearly, directly behind the carbon bond to the leaving group. So whenever we have something that gets kicked off as part of a reaction, like this bromine or bromide now, is your leaving group. So this carbon to leaving group bond, this pair of electrons attacks directly behind that bond. And this is really important because what's going on is, should we do the whole, there, yeah. So if we were looking at the bonding orbital for the carbon to bromine, we have our major nodes overlapping where we have a pair of shared electrons between the carbon and the bromine. And then this is going to be our bonding sigma bond. If we're looking at our antibonding sigma bond, these nodes are opposite, so that the major node would be in the back and the minor node in the front, and we actually can't physically share an electron between that space. This is a high energy orbital. That doesn't mean we can't put electrons here. So if we have electrons being shared between the carbon and the bromine, like we do here, and we want to start forming a bond here and breaking a bond here, get something that looks like this, where as these electrons come in and start to form this bond, that exceeds the octet on this carbon, it starts to break this bond. And as part of this happening, you get this transition state where you have this trigonal bipyramidal structure. These groups that are facing me right now get pushed this direction into this planar mode. And the way this happens is this hydroxide electrons enter your antibonding orbital. And that antibonding orbital is oriented directly behind the bonding orbital over here. So for these electrons to move into this space, we have to have a backside attack.
Drawing are the antibonding orbitals, the tiny ones.
Oh, that's just a small node.
Okay.
In drawing the mechanism, do you want us to include like that, where you drew it, where it's like
This or
Yeah.
this?
to the right?
Transition.
That?
Yeah.
Oh, we're not quite done yet.
Okay.
If you wanted a mechanism which we're explaining the resulting geometry or stereochemistry, you would need this one. If you're just asked for a general mechanism, this is the general mechanism, for if you're just pushing electrons. So what happens then is this bond fully forms, this one fully leaves, and because of that, we get back to our tetrahedral structure, but these three groups, which in this case happen to all be hydrogens, get inverted. So just to keep track of this, I'm going to call this A, B, and C, even though they're chemically identical so everyone can see that they didn't, how they're getting inverted. Little space here. So what does this mean in terms of explanatory power? Well, we see that because both of these reactants are involved in the mechanism, that's why it's bimolecular. If we have twice as much of this available, this will encounter it with the correct geometry twice as often. If we have twice as much of this available, it will encounter this carbon with the right approach twice as often. So that's why both of these concentrations impact our reaction rate. Now, we have an explanation as to why it's bimolecular. What we also see here is we see an inversion to the stereochemistry. So if this were 4 different groups, let's see here. I want to draw one. Yeah. So we have a 2-bromo substituted 4-carbon chain. That's all this is, but we're looking at the stereochemistry of the second carbon, and we can do an Sn2 style reaction by coming in right behind this carbon-bromine bond. So we could do that with, say, hydroxide. And this is going to be our product. Now, plus our bromide. What's really important to note here is that our stereo center has been inverted. So this is an R2 bromobutane, and this is going to be an S2 butanol. And this happens to be the highest priority groups for both, so that's why we see the R become the S. If you are doing this reaction on a chiral center, an Sn2 style reaction on a chiral center, you will invert the stereo center because of that mechanism. Everything's going to get pushed from one side up to a planar position, and then when it finishes, it's going to be inverted the opposite way. So in terms of predicting a product, you're not only expected to predict that there's a substitution reaction, you're required to predict the correct stereochemistry associated with it as well, if it's happening on a chiral center. If it's achiral, then you're not going to have a chiral center on the product. Yes?
The book said a good strategy was to draw the mirror image and substitute the halide for the...
And that's what this is here.
Does that generally hold true?
Mm-hmm.
Okay.
Yeah, you could, because if you draw the mirror image, you're inverting the stereo center, and then you just substitute what is going on for what left, which is what we have here. I learned it. That's a good technique.
Okay.
It's totally acceptable. I like to actually orient it if I'm doing this, so where I would say, I would probably spin this around so that this is in plane, and then do an attack, and then actually invert everything myself. But that's the way I'm comfortable doing it, because I've done it that way a lot. They're both correct.
So that's fine.
Yeah, this is fine. This is great. So the other thing that this shows is that there's an issue with, let's see here. So we've explained bimolecular. We've explained why there's an inversion of stereochemistry. What we have one more effect, and that is that it was observed that this particular mechanism strongly favors less substituted carbons. So, a methyl halide is going to react much more quickly than a primary halide, much more quickly than a secondary halide, much more quickly than tertiary. So much so that this is functionally unreactive. So this is a methyl halide, which is why it's been used in that initial example. This carbon is attached to two other carbons. That's a secondary. Still possible, not going to be remotely as fast. So why is that? Because of steric hindrance issues, right. So if we go back to our first mechanism, actually, I'm just going to use a generic nucleophile here instead of a hydroxyl. We have to have a backside attack for this to take place, which means the antibonding orbital has to be accessible for these electrons to do this attack. If these groups are small, like in a methyl's case, hydrogen, 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 very accessible. If it's secondary, hydrogen, hydrogen, carbon, still pretty accessible. Primary. Secondary, carbon, carbon, hydrogen, becoming harder to access. Now here's the caveat to this. Within these categories, except for methyl, because methyl is defined, that doesn't look too bad until you draw in the bonds for each of these as well. And you realize, okay, getting in here to the back of this carbon is going to be a lot more problematic. So tertiary is out of the question, but what if we have something secondary? Like this. Well, now we have a path to where we can sneak in and get into the back of this carbon. But these groups, what if this is like a cyclohexane ring? That's going to make it harder. So within each category, if you have bulkier groups around it, it's going to make it harder for it to access also. So you can use a little bit of common sense. If they're methyls, accessible. If it's ethyl, slightly less accessible, but still possible. If you start to get into these larger, bulkier branched groups in particular, it's going to make it a lot harder to get in behind this carbon. If you're predicting, say, which of these substrates will react more quickly in an Sn2 reaction. Any questions so far before we talk about, yeah?
Can you have a bond shift to make room for the...
A little bit. You get a little bit of distortion, but for that to happen, there has to be able to access so that you start to form a bond, so you have electron sharing, so that something's getting pushed out of the way. So the bonds aren't super as rigid, like absolutely rigid. There's a little bit of wiggle in there, but this trend still holds true where if you are trying to get a fast Sn2 reaction, that's going to be your preferred electrophile. Versus here, which you can get to work sometimes, and this is just not going to happen. I wouldn't ever bet on an Sn2 style tertiary halide. Had a question over here somewhere? No? Okay. Another one. Okay.
What about, like, if the bromine is attached to a tertiary or a secondary carbon, could you have a methyl shift or something? One of those groups?
Only the time you're looking at hydride or methyl shifts if you have a cation. That's a cation-based mechanism. So until you already have that mechanism, it's not going to take place for an Sn2 specifically. So what are some of the factors we're talking about? So we've talked about Weiss bimolecular, we've talked about inversion of stereocenter, we've talked about the steric hindrance issues, why methyl is favored over primary, is favored over secondary, is favored over tertiary. What are some of the characteristics that affect Sn2 mechanisms? We've got, if you're trying to say, given A through A, B, C, D, and E, which of these is the best for an Sn2 reaction? You want to pay attention to the leaving group, always. The quality of the leaving group is going to make a big difference. If you don't have a good leaving group, it's not going to be able to accept the electrons, which is going to make breaking that bond more difficult. So you want to have a quality leaving group, always. Halogens, because this entire chapter is based around alkyl halides. Alkyl halides, halogens are good leaving groups because by accepting those electrons, they get noble gas configuration, so they're pretty happy to take them on the way out. So for most of our examples in here, we're going to have good leaving groups. If somebody was saying, so you have ethane, you have some nucleophile. That would be a terrible leaving group because the product of the leaving group would be a methyl anion, which is incredibly basic and not stable. So this, as a product, would not be favored, which is why you're not going to see this type of reaction take place through this mechanism.
So the more stable it is with the negative charge, the better.
Yes. So the better it is at housing electrons, the more stable it is with those electrons, the better. So a really good example of a leaving group that we're going to see down the road, mostly next semester, actually in the alcohol chapter we'll start to see it, is we'll have these mechanisms where we've already seen a few of these, right? Well, if you have a nucleophile do an attack, this bond breaks, puts the electrons here, and this has water as a leaving group. So this is an excellent leaving group because obviously, because the intermediate had this charge, we put the electrons up here, made H2O, broke it off. This is very, very happy the way it is with this electrons. So we're starting with halides, but we're going to see a bunch of other things that are great leaving groups down the road. So in terms of leaving groups, pretty simple right now. In terms of other factors, we have to deal with the quality of our nucleophile. And there's going to be three factors that we should assess anytime you're looking at the quality of the nucleophile. You need to look at how basic it is. You're going to need to look at the solvent effects because how good a nucleophile is largely dependent on how good, how the solvent interacts with it, or doesn't interact with it. And then we're going to have steric effects, which take place with the nucleophile as well. Because not only do you have to have, well, we'll get there. We've got steric effects for the electrophile, but we also have to pay attention to steric effects for the nucleophile. So let's go through these real quick. Let's start with leaving groups. So leaving groups in Sn2 reactions. Let's say we've got some generic reaction where we have our hydroxide as a nucleophile, and then we've got just some generic alkyl halide. This is going to undergo a reaction. Giving us iodide as our leaving group. Now, if we do the substitution and we make this, let's see, bromide, chloride, fluoride, and everything's the same except that we've got our bromide, chloride, and fluoride is leaving groups. If we were to assess the rate of reaction here, the nucleophile is the same, the R groups are the same, the products are the same. We're going to assume the solvent's the same for all of these as well. Everything being held constant experimentally. If we call the rate of reaction for this variable, we'll call this relative rate. If this is 1, this is going to be 200. This one's going to be 10,000. This one's going to be 30,000. I was just talking about halogens, like they're great leaving groups. They're pretty good leaving groups. This isn't a terrible leaving group. It's not as good of a leaving group, even close to as good of a leaving group as these two. So I'm going to poll the room why alkyl halides, in terms of reaction rate, are ranked iodine, bromine, chlorine, fluorine. Yeah.
Because iodine is the weakest base out of all of those.
So why is that important?
Because it's more stable as I- than all the other ones, because it's larger.
It is larger. That has a big impact here. So if you were looking at pKa's of these, this has pKa of -10, this has pKa of -9, -7, and 3.2. Remember, hydrofluoric acid isn't technically a strong acid, even though it's pretty strong acid. It's not technically doesn't fully dissociate, so it's not a classic strong acid. So this is our weakest acid. This is our strongest acid in terms of HF, HI, which makes this the weakest base. And this is the strongest base. So why would the strength of the base matter in terms of its ability to hold electrons?
Share.
Hmm?
Their ability to share electrons.
Right. Exactly. And so you have how basic it is, which is our first point. But the other point that came up here is the size. So fluorines are really small. They're really electronegative. They're the most electronegative, but they're also quite small. There's not a lot of room to house more electrons around them. So even though they really want their electrons, they just don't have that much room to bring more electrons to the party. which is why the electrons get a little bit crowded when we add that extra electron to it and come up with a fluoride. That's really the reason why we have this positive pKa versus a negative pKa here. As we get larger and add extra layers of electrons to these, there's a lot more room around the nucleus when you get further away to put another electron. It's quite a bit easier to do that. So that's the second reason why iodine and bromine are preferred halogens if you're intending to set up a good Sn2 reaction. If you said, hey, as a free response question, set up a good Sn2 reaction for synthesizing something, you would want to use bromine or iodine if you had a choice, which in that kind of question you do. So that's the leaving group. Any questions about leaving groups as pertains to alkyl halides, which is the only leaving group we're looking at in this chapter right now? Okay, so nucleophile. For Sn2. If the attacking atoms are the same size, so everything being held relatively constant in terms of size effects, the stronger the base is going to be a better nucleophile. Something very, 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 there's exceptions. There's a lot of it. There are exceptions to this, and we're going to talk about exceptions a little bit. But if something is great base, it's going to tend to be a great nucleophile. Because what's a base measure? If something's a strong base, what's it want to do?
It wants to share.
It wants to share its electrons with hydrogen. And something's a great nucleophile, it wants to share its electrons with an electrophile. So it just so happens that that's also an electrophile. So there's some overlap in terms of the rationale for between what makes a great base and makes a great nucleophile. So with size being the same, stronger bases, stronger nucleophiles. Good example, really strong base we were using at the end of last chapter. Very, very strong base, similar in size to hydroxide, but more basic. So if we were ranking these in terms of their relative basicity, most basic, still pretty darn basic, not as basic, but still basic. Same trend holds for nucleophiles. Best nucleophile, intermediate nucleophile, still a great nucleophile, but not as nucleophilic as the first, less nucleophilic.
Why do you have two negatives on?
Oh, because I forgot that I put a negative there.
Okay.
Because it's extra negative day. I was going to say two negatives make a positive, but that's actually patently untrue in chemistry, so we are not going to roll with it. So what happens if the size is different? Let's do something like which one of these is a better nucleophile right off the gate, based on what we've already talked about? Iodine, right? And that has to do with its effects from how much more basic it is. And then we also have effects with it having electrons more distant, so it's easier to give those electrons up because they're not held as tightly to the nucleus, which impacts its being a better base. But we also have to take into account the ability of those outer electron clouds to be distorted. So if we need to do a backside attack on this carbon, it's a lot easier to do that if we can distort those outer electrical clouds because they're not held as tightly. What that looks like is as if this is fluorine, it has to get closer because it's smaller. It has to get closer to this carbon to overlap orbitals. Because one, it's smaller, so it has to get closer, but also because as these electrons start to move into this antibonding orbital, they're going to cause a little bit of distortion to that electron cloud. Fluorine holds its electrons so tightly that it's hard to distort that cloud, so this fluorine has to get even closer to this carbon for this reaction to take place. Iodine is much larger, and because its electrons that are in its valence shell are much more distant from the nucleus, it's easier to distort those as part of the bonding process. So without the iodine nucleus getting as close to the carbon, it can initiate the reaction just by virtue of distortion of its electron cloud. So I thought of a joke, but I'm not going to tell it because it's distasteful. It's too early for that, and everyone's right. So how basic something is matters when size is not an issue, but size is an issue also. Any questions so far? We have one more effect to talk about. No questions about relative basicity or size for affecting nucleophile strength? Yes.
Should we know the approximate pKa's of those, or just the relative basicity?
Relative basicity. But for halides, you're going to know you know how they're ranked based on their size. And if there's any question, you should know that hydrofluoric acid is your only hydrogen halide, which is not a strong acid, which means it's going to be your weaker acid is going to be your stronger base. The other effect here is the solvent. And this is a huge, huge, huge impact. When we're doing these kind of reactions in OChem lab, if we're doing an Sn2 reaction, we are going to be dealing with polar aprotic solvents. I went through the book and I was really trying to find this particular explanation in the book didn't really align with the way I've seen this explained previously. Usually people in the textbook will just come out and say, if you're doing an Sn2, pick a polar aprotic solvent. It has to be polar because we are liberating anions into solution. If you have a non-polar solvent, it's very hard to put charges into solution, and that makes the leaving group lower quality leaving group. So we really have to have some degree of polarity for these reactions to take place. So I'm not going to do this in hexanes. But it needs to be aprotic. And we're going to talk about why in a second. So this is what's favored. The book goes into a large explanation about how polar aprotic solvents affect nucleophiles one way, and polar protic solvents affects the relative basicity another way. But I don't think at any point in the book do they say, this is what you want to use when you're setting up an Sn2. So polar protic solvents, I'm just going to say equal bad for Sn2. And the reason is because what these effectively do is they quench your nucleophile. If you quench your nucleophile, it's really hard to do a nucleophilic substitution reaction of any kind for Sn2. We'll find there's ways around this with Sn1. So examples of polar protic solvents would include
Water.
Alcohols. Those are the most common, right? Polar aprotic solvents. Oh, let me get rid of this sheet. Acetone is a polar aprotic solvent. It's a ketone with a pair of methyl groups. We also have acetonitrile, which is a methyl group attached to a cyano group. We've also got DMSO, dimethyl sulfoxide, phenomenal solvent. Note the similarity to acetone, except that it's got a sulfur in the middle. Dimethyl sulfoxide is phenomenal with dissolving things. If you ever work with it, there are certain cautions you have to take into consideration. One is spectacularly transdermal. So if you dissolve something in DMSO and then you spill it on your skin, whatever was dissolved in the DMSO is now in you. So DMSO is used for veterinary and drug delivery. I think it still is, even though it's a little dicey to use it safely. Because if you get it on yourself, then you've delivered the drug on yourself. It has an amazing way of wiggling through all kinds of things, including it'll work its way through a nitrile glove if you give it enough time. So even if you're gloved up and you get it on your gloves, you have to swap them really fast. They used to rub DMSO on athletes' joints because this is actually a really good sulfurous precursor to building up your cartilage. They stopped doing that because whatever was on your skin got into your joint. Yeah.
Is that something they use for like nicotine patches or whatever?
Yeah, and also illicit drug use in general. So there's all kinds of methods. And now so that's one major consideration when you're using DMSO. The other is that it's not volatile. So removing it, if you do a reaction in the solvent, getting your product out of the solvent is really challenging. And the books will say, oh, you just do some column chromatography. It's not really easy. They lie like dogs. Everybody who's done it knows. I've had too many reactions in my life where nothing else quite works, so we have to use the DMSO, and then you just go through an enormous amount of work to remove it from DMSO afterwards. So, fantastic solvent, getting things in, really hard to get the solvent off. And then we've also got DMF, dimethyl formamide, which looks like that. Ooh, might as well. Right. Two up top, too. So these are all fantastic polar aprotic solvents if you wanted to do a reaction which really keeps the nucleophile acting like a great nucleophile. I keep talking about quenching. Before we talk about quenching, which is not the term the book uses, I think it's easier to visualize what's taking place. Any questions so far? Yes?
Chloroform, is that a good solvent? I hear a lot about chloroform in organic chemistry.
Right? Organic chemistry lab, the only place where it's really appropriate to ask, hey, where's the chloroform? Ask the chloroform, please. Chloroform is a great solvent. It's a great solvent also. It's not, it's little polar. It's not strongly polar. So chloroform is polar, but it's way more polar than, say, hexanes or something like that, but it's not going to be as polar as these groups with your lone pairs and your larger net dipoles. But it's a great solvent to work with. You just don't want to inhale it. That's one of my most. I've inhaled so much chloroform. I never was like, that makes sense. There was an accident in the lab. I was working with an undergrad in this hood, and we were rotovaporizing chloroform in this hood. And so the hood's running, and the rotovap pump is running. It's quite loud. And somebody thought it was a great idea to turn off all of the power to all of the hoods in the building.
Oh, no.
But they didn't notify the people working in the labs when they did this. Now, normally, when you do that and you lose airflow, an emergency alarm goes off, very nice audible alarm. But when they killed the power to the hoods, they also killed the power to the audible alarms. So we're sitting there, like, removing a few gallons of chloroform in a condensed space, thinking that the fumes are going up, but instead they're just accumulating in the hood, with us standing in front of the hood like, And it's like a frog getting boiled. It sneaks up, you don't smell it, because it starts low and creeps up. It's not like this, bang, you get hit with this huge amount of chloroform right away, where you, oh, this, I've got chloroform in my face. All I remember is sitting there watching the rotovap spinning with the undergrad, and she's just entranced watching this thing spinning too. And in slow motion, the lab safety manager comes in the room to our side, and it's just like a movie, like, no, like shutting the sash and like, hi, Emily. Hi. So, worst, like you could feel your liver pulsing for 3 days as you tried to get rid of it. It's just like so awful. Terrible hangover. Like just so toxic and vile. But yeah. Not my worst lab accident, but one of my more hilarious. Because it worked. I hope I don't get cancer. But that's the truth. Is that there's this, like, chemists have no sense of humor, which you're fully aware of at this point because you've tolerated me for a few weeks. But the joke is that organic chemists die very slowly and inorganic chemists die spectacularly. And there's some truth to that. So, sorry, I diverged with something fun for a second, but now we have to stop having fun because this is chemistry and there's no fun allowed in chemistry. Any questions regarding this other than chloroform? Somebody knew. It's like, man, if I get him talking about chloroform, we get a break. Well played. Well played.
Not what I was going for.
Oh, okay.
Turned out pretty well.
Okay. I can't even remember where you are. Oh, yes, steric effects. Oh, quenching. Quenching. Any questions before quenching? Okay. Let's talk about quenching. So, if you have methanol, and we've got iodide here, because it's the solvent, it's going to be all over the place. Y'all get the idea. This is going to have a partial positive charge, partial positives, all around this negative charge. This negative charge, this extra electrical density, is why it wants to act as a nucleophile. However, if through interacting with all these protons, all these partial positives satisfy this negative, it no longer has chemical rationale to act as a nucleophile. It's now supported by the solvent. So by putting this into this polar protic solvent, this is no longer a good nucleophile. Whereas if you put it in a polar aprotic solvent, which doesn't have this accessible partial positive charge, it retains its nucleophilicity. So you say, yeah, but Dr. McGill, this has a partial positive charge here on the carbon. You'd be correct. However, it has these methyl groups which make it less accessible. They can't crowd up around the nucleophile as a solvent in the same way. And the accessible part is partial negative charge, and it does the opposite. It doesn't quench that negative charge. If anything else, it kind of potentiates it a little bit. So polar aprotic solvents, good for SN2. Polar protic solvents, bad for SN2.
Okay, so we're saying, wait, so we're saying, oh my gosh, is that it? No.
No, that's a ketone.
Sorry. We're saying the ketone's fine to use.
Because it is a polar aprotic solvent.
It's a polar aprotic solvent because it has those methyl groups that keep, that block.
Well, it's
the
polar aprotic because it doesn't have this exchangeable proton on it.
Okay, oh, okay, okay, that makes sense.
None of those have exchangeable protons.
Okay.
You can't pull the protons off of those methyls. So the last variable here with the solvent is you need a solvent that doesn't have steric effects. So excuse me, not the solvent, a nucleophile. So we were using hydroxide as a nucleophile. Great nucleophile. You could also use any alkoxide, like methoxide, as an excellent nucleophile for an SN2 reaction. So deprotonated alcohol, fantastic. Deprotonated water, fantastic. Most of the time. An exception would be something that's extremely basic, but does not act as a great nucleophile in SN2 reactions, and this is butoxide, which is T-butyl alcohol. When T-butyl alcohol is deprotonated by a acid, you get T-butoxide. This is very basic, very strong base, but because of all this bulky group, it has a very hard time acting as a nucleophile in an SN2 reaction. So if you're being asked which of these would be ranked as excellent nucleophiles for SN2, this would be one of those exceptions because we have all this bulk around the point of reaction, which makes it very hard to access a back-end attack. That is it for variables impacting SN2. Quick summary This is an incredibly useful tool, incredibly useful synthetic tool. And if you have some generic methyl or primary, this is great because it's primary alkyl halide. And you can react with so many different nucleophiles. You can use hydroxyls, you can use alkoxides, you can use the sulfurous equivalent, you can use sulfurous equivalent of your alcohol, you can use ammonia, you can use cyanide, you can use, we've already done this one, alkyl anion, and we can make tons of categories of products. We can make alcohols, we can make ethers, we can make thiols, we can do thioesters, we can do ammonium salts, primary ammonium salts, we can make nitriles. And this is also just making a new alkyne with a carbon-carbon bond. So we have a huge diversity of different products we can make using Sn2 reactions. So my recommendation is play with these things. Run a lot of problems around identifying what's a good Sn2, what's poor Sn2 for all the different variables. Discretely, it's not that hard. When we start to combine elimination as a possibility that goes in conjunction with substitution, it gets more complex. So you want to get real comfortable with these pretty fast. I will get the homework and extra problems posted during office hours unless we have people at office hours, which the week after tests is a coin flip. Let me